Good evening, everyone. I am Bandhuka, Technical Events Coordinator for Civil Engineering Sectional Committee. And today is the 15th session of our lecture series on structural design of highway bridges. And our sincere gratitude to Professor Tisanjaya Sinha for conducting this valuable lecture series. And for the participants, please add your membership number as well along with your login name so that ISL can trace your participation. Over to you, sir.
Thank you, Bandhuka. So last time we talked a lot about pile foundations. So today we'll see how the computer modeling can be done, and there are various theories that we should know to do computer modeling. So we'll concentrate on some of the important ones today. Right. So last time we talked about the pile foundations. So if we take a bridge, we'll have the abutment which can rest on piles like this, and we also can have the piers that can again rest on pile foundations, and then so there are many items that we have to design in the substructure and foundation. So first we look at the pier. So now we are going to look at the pier. So first we look at piers. So if you look at, I can take one example of a bridge that we were involved, and actually it's a flyover. So the original design was something like this, and it had a wide pier, and then it was on piles. So they had about 10 piles as far as I can remember, like this, each 1 meter diameter, and the cantilever part is small. Then I can also relate the story of Southern Highway, and Southern Highway also had similar bridge piers, which had the shape like this, and then it was also on pile foundations. But in Southern Highway they have used precast piles, 0.4 meter by 0.4 meter precast piles. Generally, I do not agree with using precast piles, because in the case of now we have bedrock, weathered rock, fractured rock, and then we have basement rock. So when we are doing the piling with cast in situ board piles, we can actually go deeper into the basement. But in the case of precast piles, we are most likely to end at this level. So now this will be pretty good against covering, whereas this is not a very good solution against covering, because we are having tropical climatic conditions, and also we have to be concerned about the climate change. So in current context, considering the kind of equipment we have, it might be a good idea to go for this solution than using this solution. But Southern Highway was planned nearly 20 years ago. So things, the knowledge, the level of knowledge and experience could have been different. Now, so in this, so what happened in Southern Highway was, there was a little kind of dispute between the designers and the consultants. And so in this cantilever part, most of the reinforcement were curtailed at a particular section. And if you look at Euro codes and all the codes, generally, you know, we are discouraged to curtail a lot of bars at one section because they can be stress concentrations. So what happened was there were cracks like that. And then this was at the latter part of the project. So somewhere like 2010, 11. So it was thought, okay, now this is little, you know, the need to complete the project was also there. Then they thought, okay, let's have something like that. So what happened was they excavated the soil here, and then they discovered that, you know, all these piles cracked, pile caps have cracked in a very significant way. And later we attributed it to delayed ettringite formation, but it was not 100% sure, but it looks like that it is delayed ettringite formation. So then all these, you know, lot of remedial actions had to be taken, and you know, finally the piers look like this in most of the bridges. So when you look at pier like this, in the modern day, now we can have other variations. So one of the other variation is, well, let's have something like this. With a narrow pier capping, pier with a narrow pier. But so these cantilevers can be about 3 to 5 meters or even 3 to 6 meters. So when you have large cantilevers, now in this range, reinforced concrete might work. But when you are going for this range, you have to go for pre-stressed concrete. And you might have to again do the pre-stressing in 2 stages, and you might ask why. The reason is when you look at the loading system may be something like this, very heavy loads. So that means this will need heavy pre-stressing as well. But in pre-stressing, we have to see the stressors at transfer. So when you look at the stressors at transfer, you'll find, now when you provide the tendons like this at the top, what will happen? Now this is going to bend like this. And who is there to suppress this? Only the self weight of this. So which means your ability to apply pre-stress is limited. So you can apply only limited pre-stress. You can apply only limited pre-stress. You can't apply the desirable pre-stress. So that is one of the problems you are going to face. So, so what is the solution? Then the solution is you will apply limited pre-stress. Apply limited pre-stress. And then you will bring all the beams and place the beams here. Now, when you apply the load of the beams, what will happen? Now, the weight of each beam can be about 100 to 150 tons. What will happen? All this will become level, but still unable to carry the live load. Unable to carry the live load. So what are we going to do next? We are going to apply, we can apply additional pre-stress like that. So that is the second stage. And when you apply this pre-stress, now we don't have a problem because we have enough weight to counteract the uplifting due to pre-stress. So if you look at this type of situation, what can you say about this structure? This is a cantilever. So cantilever is a statically determinate structure. So if we are going to have a cantilever and if it is statically determinate structure, what can we say? Do we need computer analysis? Based analysis? Answer is no. No, we don't need. The structure is statically determinate. However, if you look at a pier capping beam, pier and pier capping beam like this, we might have to consider a situation like this. So if you look at the dimensions of the pier can be about 4 meters to 6.0 meters. The width can be about 1.0 to 1.5 meters. So it can be in this kind of range. And then we are also having a beam like this. So what are the ways that we can, if you really want to create a computer model, what are the ways that we can create a computer model? So that's a question we have to ask. So one possibility is to consider, now if you look at the pier capping beam from above, and this is the pier, and pier capping beam can be wider than the pier. So it's maybe about 2 meters in width, because you need enough space for keeping the beams. So the beams might come like this. And then you have to create a diaphragm connecting them. Depending on the type of connection, you might have to do something to ensure that the bearings can be properly placed, and also this continuity is taken into account. So which means you need space. So how are we going to, if we like to have a computer model, what are the options available for you? So let's see what are the options available. So one of the possibilities is to create a truss. Like that. And then here also you can have 2 columns and then connect them with a moment resisting frame like this and create a structure. And then we can create another structure. Same thing, connect them at these locations. So you can, so when you look at the force in the top chord, it's in tension, and this is in compression. You can get an idea about the bending moment. So that is one of the possibilities. So only thing is, because it is statically determinate, you can get these forces, but there are certain forces that you like to get some idea. What are those? And those are the forces during construction. Those are the ones that occur during construction. So one of the possibilities that you like to get some idea is, we have placed one beam on this side. So the beam is placed on this side, but there's no beam on the other side. How this structure will behave? You might like to get some idea. And now you can see it is subjected to a bending moment this way and a bending moment this way. So manually also you can get some idea, but if you create a computer model, you might be able to get a better idea of the type of moments that will be induced in the structure by looking at the forces, because when you have a moment in a structure, what will happen when there are two elements and like a truss, and then you have a moment, this will go into compression, this will go into tension, and then you can easily work out how much moment is transferred here. So there are easy calculations that you can perform. So if you have a computer model, you can get a good idea about the behavior, because sometimes what happens is, you will find that the pier is like this, the other pier is like this, and you are going to place one beam. Now another beam is placed here. Sometimes the next beam might be brought on top of this beam that has already been placed, because you have to erect some rails and transport the other beams. So there can be so many different combinations that you might be interested, and I can just show you one or two such situations that might arise by showing some of the situations that we got during the construction of Orugodawatta flyover. And so we'll share the screen now. So share. Right. Now, if you look at this particular bridge at Orugodawatta, now this is the kind of beams. These are the kind of beams that we used, and because the original design was a box girders, the box girders of about 1.35 meter depth. Even with these beams, we had to match the original depth, because we had to ensure that the profile of the road, highway profile, has been maintained. So we use that, and so I can go further and show you the situation. So these are the kind of beams. These are how they were cast, and these then block, and these how pre-stressing was done with all the barrel and cone type anchors, right? And then now these are the kind of beam, and you can see it's not very tall. It's not it's smaller than the height of a man. And now you can see bridge beams are being arranged for lifting, and these are the kind of lifting girders that the Chinese contractor use. Not very sophisticated, but they were very effective, because they use jacks and lifting equipment. And here you can see how they lifted it up. And here you can see the situation. Now here you can see, now this side nothing. This side you are getting beams. So that's a kind of serious situation that can arise. And you have to be aware of these situations when you are interested, when you are involved in the substructure design. So it is not just the completed bridge, but you have to think about what could happen during the construction. Now here you can see a lot of beams are kept on top of the ones that have already been launched. So that is that's a type of situation. And then when all the beams are placed, then the situation becomes very favorable because the loads are now balanced. Whereas during the construction, the loads may not be balanced. So you might find a situation where you are loading only one side of the pier capping beam, and in doing so you are loading only one side of the pier. And here you can see some prop also has been placed during the launching operation, because they can be very high loads on one side of the pier. But these are the situations that you might like to do computer analysis. So how can we do computer analysis for this type of situation? So that's what we are interested in seeing. And then, now things are getting better. Why? Because you have a massive load and it is well balanced, almost fully balanced during when there's no live load. But with the live load, again, it can become unbalanced. But when you compare the live loads with the weight of the bridge, you might find that the live loads are not very significant unless you are going to get one container truck after the other. But most of the other highway loading may not be that significant. And also, even in that case, you need kind of a traffic jam on one side of the deck, because these are 4-lane decks. So on one side, 2 lanes are full of traffic, other side is empty. So that type of situation would be needed. So basically, when you are doing the substructure, you can see there can be very serious situations that might arise, and you might need to pay some attention to those situations. So how can we do all these things? Because when you try to do manual calculations, you can get reasonable answers. But in the modern computer era, most of the engineers like us to present our calculations in the form of computer modeling as well. So in such situations, what are the options available for us? So that's what we are going to discuss today. Right. So if you look at the deck, analyzing a deck is not a major problem, because you can always create a grillage and apply the loads, find the bending moments and shear forces. And you can apply any kind of load onto the deck by using the transverse members. Generally, we prefer the application of the loads on the transverse members than the longitudinal members. Because when you apply the load on the transverse members, you can actually bring the load very close to the actual location of application of load. Whereas when you are applying the loads on the longitudinal beams, you might not be able to be very accurate. So because of that reason, here you can see all these loads are applied. Most of these loads are applied on the transverse members, unless we have the provision for applying them accurately in the longitudinal member. So here you can see it's a transverse member. And here again you can see they are all applied on the joints, but at the transverse members. And here again you can see the kind of HB vehicle. But here you can see the HB vehicle has come pretty close to the support. Now here we like to see the maximum shear effect on the deck. Whereas here we like to see the maximum bending. To get the maximum bending effect, we keep the very extremely heavy vehicle in the center, close to the center. And to get the maximum shear effect, we place the extremely heavy vehicle pretty close to the support. But again, we can't place the vehicle as it is because the vehicle is well defined. The moment you place the front axles at one location, the rear axle locations are automatically decided. And here again, I think I have applied the loads maybe on the, looks like I have applied this pedestrian load on the H-beam because most of the pedestrian pavement would have come on the within the H-beam area. And then you can get bending moments, shear forces, and torsional moments. So basically, although for design a big deck, you might have to do a lot of calculations. These days, when performing structural analysis is not a major problem because the moment you create a grillage and apply the loads with reasonable accuracy, you can always end up with a acceptable value for bending moments, shear forces, and torsional moments. So that is not a major problem. Now today we are going to see how we can do the modeling for foundations. And again, I'm going to show you another note, and that is now I'm going to share again. Now I'm going to share again. Right. Now this is about modeling the foundation, the soil with different characteristics. Right. So for that, I have to tell you a little bit about theory, and also I would like to show you some model that I have done recently so that you can get some idea about what we can do. So just give me 1 minute until I get this SAP 2000 opened. Right. So until we get that going, so let's see what is the situation. Now let's look at again the historical background of Sri Lanka and India and all these countries, and I have already explained we are having laterite soils. So laterite soil is a mix of clay, silt, sand, and gravel. Right. So when the water table is low, laterite soil behave more like a sandy soil. And when the water table is high, it behaves more like a clay soil. Right. Now I'm going to show you two different situations that can arise. And when we have sandy soil, we can use Winkler spring method, Winkler spring method. When you have clay soil, we can model the soil with solid elements. We can model the soil with solid elements. So I'm going to show you the kind of theory that you should know to undertake this kind of modeling. And before that, I would like just to show you two models of buildings that might be of interest to you. I'm opening the models. So in a moment, I'll show the models. It will take about 1 minute to open the models. So I'm going to share the screen now. I'm going to share the screen now. Now you can see a building with a cellular rock foundation. And here you can see, if I get a enlarged view. Now here you can see it has a cellular raft. So you can see some compartments, and within that is hollow. And here I have put it on springs. What is the idea? Idea is, it's a kind of sandy soil formation. So basically it's a laterite soil formation with very low water table. Therefore, the laterite soil is going to behave like a sandy soil. So I should be able to represent the behavior of the soil by using springs. And here when I say I'm going to represent the behavior of the soil by using springs, what I'm saying is I'm going to indicate the short-term behavior. This is not the long-term consolidation, settlement or anything. This is the elastic deformation of the soil that I'm going to show. This is only the elastic deformation of the soil that I'm going to show. And with the elastic deformation, we can get the reaction on each spring, and that will give an idea whether the bearing capacity of the soil has been exceeded or not. So that's what we are going to get from a model like this. Now I'm going to show you another model. So I'll open another model. And that is now you can see if the water table is high, the same building with cellular raft. Now what do you see? Now what you see is not only the cellular raft, I have modeled the soil as well, and I have used solid elements for modeling the soil. So we'll take one of the examples and see how all these things can be done for a bridge foundation as well. May not be today, because today I'm going to cover the theoretical aspects of it. And I'm also going to show you how a model of this nature can be generated as well. So that you, on your own, you will be able to create models like this. But at the same time, another day I'll do a demonstration for you, so that you will get some idea about, a better idea about how to create a model of this nature. So here you can see, now this part is the soil, and here you get the cellular raft, and here you get the building. Now to avoid a lot of confusion and complexity, in this particular building, I have considered that it's a frame building without a shear core. It's not a usual case, because when you have shear core, you will have many other extra complications when you try to do the foundation modeling, because shear core will not be a regular shaped structure. So you need some special attention whenever you want to model a cellular raft. But anyway, there will not be a cellular raft directly under the shear core area, because you will only get a raft, not a cellular raft. So I can also show you how a raft can be modeled, not the cellular raft, and we'll have a look at that also. And now the same building, what you see now is the same building. Now it has a soil, but only the raft, thick raft. And so the underneath the building, what you get is a raft foundation just surrounding the building. And this raft foundation is now sitting on the soil. The raft foundation is sitting on the soil. So you can create models like this as well. So similar models can be made for bridges as well, bridge foundations, superstructure, substructure, as well as foundations. You can create similar models depending on the level of water table, type of foundation, and also the type of soil available. Right. So with that, I'll stop sharing. Or else I can actually show you another model, but just a demonstration only. And that is a model with the pile foundations. But again, so here you can see the superstructure and substructure all model together with pile caps. And here you can see the pile caps. So we can now this is again maybe relevant to us in the bridges, because we are modeling pile caps, and I can just change the view to so that you can see how we have created the pile cap. And now you can see how the pile caps have been created. But again, you can see I have not done meshing of the pile caps. I have kept without meshing, and when I do the meshing, I can get more accurate results. And from each pile, we get if I go for this particular corner, if I concentrate on this particular corner, you can see how it goes. And here you can see one column coming above, and then we have a pile cap, and from the node points of the pile cap, we are getting the piles going down. Now in this particular model, I have not modeled the soil by using springs. Instead of that, I have considered that the soil exists, but I'm not going to worry too much about soil, because soil is firm, and because of that reason, I don't have to worry too much about buckling of the piles. So in that, to represent that particular situation, now you can see I have considered that this is only a mathematical model of a building, not the real building. So what am I modeling using a mathematical model? I am modeling only the behavior of the building. So what is the behavior of the building? Behavior of the building is at the ground level, the deflection is 0. So here I am making sure by having some additional supports, I'm assuring that the deflection of the building is 0. So what we have to always keep in mind is, when you are doing modeling, computer modeling, our computer model is a mathematical model. So a mathematical model might look very different to the actual structure. So always you have to keep that in mind. So I'll stop sharing so that I can go back to the theory part. So let's see how we can model the soil when it is sandy. So when the soil is sandy, let's take a foundation, inverted T-type foundation. Just as an example. So let's say we have a building on an inverted T-type foundation. And it's a weak soil, so we have gone for an inverted T-type foundation because it's a very efficient foundation system. So now we have a foundation. So how can we represent the soil? Why do we want to represent the soil? We want to see these loads are acting as point loads, and we are keen to see whether the bearing capacity of the soil is exceeded. So we can make various assumptions. On the other hand, we can really model the soil with so that the stiffness of the foundation will decide how these reactions will vary. So what we are going to do is we are going to apply a series of springs. So what we do is we'll divide this 1 into 1 meter or 0.5 meter segments. So this long foundation is divided into segments. And each segment, center line to center line, will be represented by a spring. And the spring should represent the soil characteristics. Now let's say we have a soil with 150 kilonewtons per meter square bearing capacity. Now, do you know what is the meaning of this? When I say the bearing capacity of soil is 150 kilonewtons per meter square, what is the actual meaning of that? The actual meaning is, if I apply a load of 150 kilonewtons per meter square, so 1 square meter, so there will be certain elastic modulus of soil, and we know deflection is related to the elastic modulus, and the corresponding deflection due to this elastic modulus, whatever the value available with the soil, will be limited to 25 millimeters. 25 millimeters. So using this particular theory, in textbooks you can find the subgrade reaction of soil is they have given an empirical formula which says it's 40 times factor of safety multiplied by bearing capacity. So generally factor of safety can be 2 to 3, and bearing capacity is whatever the value that is given. In this particular case is 150. So the subgate reaction is 40 multiplied by, let's say I'm going to use a factor of safety of 2.5 multiplied by 150. So I'm going to get an answer of 40 multiplied by 2.5 multiplied by 150. So I'm getting a value of 115,000. And then the most important thing is, what is the unit? Kilonewtons per meter cubed. Now, what is the meaning of this? Because when you look at a spring, you apply a load in kilonewtons, and then spring constant is given in kilonewtons per meter. But here we are getting, the textbooks are giving us a value of for subgrade reaction, vertical reaction to represent the soil, but the unit is in kilonewtons per meter cubed. But it doesn't matter, because what we are saying is we are going to have a inverted T-type foundation. I'm looking at the plan view. So when you have a foundation, it might have a width of 2 meters. And if I'm going to get springs in 1 meter interval. So each spring will represent 1 meter by 2 meter area. So then what I have to do is, to get the spring constant K, I have to multiply Ks by area. That means 15,000 multiplied by 1.0 multiplied by 2.0. So I get 30,000. So the spring constant that I have to substitute in the computer program is 30,000 kilonewtons per meter in the vertical direction. So it is 30,000 kilonewtons per meter in the vertical direction. So that is the theory. So Winkler spring method is a pretty good method and very I would say a very useful method, but may not be extremely accurate, but it gives us a good opportunity to see how the load applied at various locations can be distributed depending on the stiffness of the foundation. For example, we can have two types of two inverted T's. One is like this, the other one is like this. So these bases may be same, but this may be about 0.6 meters, this may be about 1.2 meters. And the moment we look at 1.2 meters, we know 1.2 meter one will give a better load distribution, but of course at the same time we have to be concerned about the cost. So by allocating different values for these spring constants, we might be able to have a situation, because if you look at the actual distribution of loads, what should be the actual distribution? Actual distribution is, we should have a situation where we have higher stresses here, lower stresses here, higher soil stresses here, lower stresses here, higher soil stresses, and all that. So this is the real distribution we expect. But if the foundation is firm, we might find that, you know, it flattens. It flattens. So by allocating different sizes for this inverted T-beam, the stiffness will not change. We might be able to see how the reactions vary, and reactions will give an idea about the load on the soil. And if we like to see that the load on the soil is fairly well distributed, then we will need a stiffer foundation. And to experiment with different soil parameters, and also to see what the kind of stresses that occur, we can actually change the stiffness of the foundation easily by using Winkler springs. Because sometimes you might find here you might get 170. But when you increase the stiffness of the foundation, you might find it drops to about 100. So you might find that, you know, by increasing the stiffness of the foundation, you can easily satisfy the bearing capacity without increasing the width of the inverted T-type foundation. On the other hand, you might consider increasing the width is better than actually, increasing the depth of the foundation. So it's all up to you. But with this Winkler springs, we are providing you with a tool to do experiments in a very short time, because it will not take a lot of time to do these experiments, because once you make the model, you can change the shape of the beam. The depth of the beam can be easily changed within 1 or 2 minutes. You can do it, rerun it, look at the results, and you can make you can you can have a lot of interesting experiments before we select the actual parameters for the building or the bridge under consideration. So Winkler spring method is fairly straightforward, but it's a very useful method. May not be extremely accurate, but it gives a reasonable accuracy. So that is one way of looking at it. Now we have to see, when you are doing a model, and let's say we are having pile foundation, and we have done a model using that kind of trusses, and here you might consider some situation like that. So there are so many different ways you can make a model, and you might have some elements like that for stability, and then you might have foundation here, and let's say 4 piles, and then you might have a situation where you might have on beams only on one side of the bridge, and sometimes we might be bringing other additional beams on top of this. So you'll find that a lot of beams are on the foundation or on the bridge, but unbalanced, fully unbalanced. So how the foundation is going to respond? But when it comes to the vertical load carrying capacity, you are pretty sure that you know, because you have done some reasonable socketing, and then there's some fractured rock as well. That also can give good skin friction. So you are pretty sure about the piles. But what is not sure is how these piles are going to behave when they are subjected to bending. Now you can see the whole system is subjected to concentrated loads acting somewhere there. So how is this going to behave? And for that, we have to actually see. Now we can apply some horizontal springs. Okay. For that, we need to know the subgrade reaction, but this time horizontal subgrade reaction. Now we like to know the subgrade reaction, but this time it's the horizontal subgrade reaction. So how can we find this term? For that, again, there are theories, and we are going to look at these, simplified theories that are available, right? So, modulus of subgrade reaction for clay soils. That means the water table is high in this area because this is a river. We are considering a bridge. The river is full of water. The water table is high. Though we have good soils, good soil having sand and clay mix, it is going to behave more like a clay soil. So we have to see what the type of soil is available. Sometimes when you have clay soils, you might they may not be fully of laterite origin. So you might find they are really weak soils, like SPT less than 2 means it's very bad soil. But you might get the situation SPT of 2 to 4, again pretty bad soil, but not the worst. But when you get SPT of 4 to 8 in clay soils, we generally say they are reasonably firm soils. And when the SPT value is 8 to 15, we call it stiff soils. And when it is 15 to 30, we call it very stiff soils. And when it is greater than 30, we call it hard soils. So basically, a lot of testing has been done to determine the cohesion of soil, and cohesion of soil can be related to, when you do a lot of testing, you will find cohesion of the soil comes pretty close to 4.5 to 5 range. So sometimes cohesion of soil is given as 5 times N, and I prefer to use 4.5 times N. But many geotechnical engineers use the cohesion is equal to 5 times the SPT value, 5 times the SPT value. But if the SPT is like 2 to 4, I mean, you have to be very careful, because sometimes the SPT that is reported may be misleading. But if it is, when it is greater than 4, generally, you can rely on the SPT value. Now, let's say we are having a SPT of about 15, which means the cohesion of the soil will be 4.5 times 15. 4.5 times 15, which comes to about 67.5. On the other hand, you can also say it's 5 times 15 and use a value of 75 also. No harm. So, because when you look at this one, you can see even if you use a value of 5, there are a lot of results falling in that region. But if you use 4.5, it may be even better. So,
so
this is,
yeah. So screen is not shared, sir.
Oh, sorry. I just one moment. I will. Sorry. Now you can see, when you have SPT value, less than 2, you get very soft soils. 2 to 4 soft soils. This area, the SPT values can be much variable. So you have to be concerned about it. And then SPT value of 4 to 8 is firm soil. 8 to 15 is stiff soil. And 15 to 30 is very stiff soil. And if it is greater than 30, it's hard soil. Then the cohesion is given by 4.5 times SPT value. And how do you get it? These are actual lot of results they have plotted. And from that, you can see a value of like 4.5 to 5 is pretty good. Geotechnical engineers, a lot of geotechnical engineers use cohesion as 5 times N, 5 times N. And it can be even 4.5 times N or 5 times N. And once you know the cohesion, the horizontal subgrade reaction for clay soils is actually given by equation like this, the horizontal reaction, and where Ks is the modulus of subgrade reaction in kilonewtons per meter cubed, and Es is the elastic modulus of clay soil. Now we have to find Es. B is the width of the pile. IW is an influence factor which can be taken as 1. And nu squared is Poisson's ratio. Poisson's ratio is 0.3. So nu squared is 0.09. 1 minus nu squared can be taken as is 0.91 something. So we generally take it as 1. So which means this is 1. IW is also 1. If the width of the pile is 1, the horizontal reaction in kilonewtons per meter cubed is equal to the elastic modulus of soil. Elastic modulus of soil. Then the question comes, how are you going to find the elastic modulus of soil? For that, depending on the overconsolidation ratio, you have to find ES over CU value. And generally, again, you have to look at the type of soil. You can see plasticity index less than 30 is a good soil. 30 to 50 is bad soil. Plasticity index is greater than 50 means extremely bad soil. So generally, if you are going to, you might have one of these, or you can even have this. But again, you have to look at the overconsolidation ratio. Historically, most of these soils have been subjected to various stresses, especially if you are in the European countries, then European countries have been covered with ice caps historically. So the over-consolidation ratio for European country can be greater than. Even in Sri Lanka, I mean, it may be good to use a value like 3 to 5, because we, unless you know for sure that the soil has not undergone over-consolidation. Over-consolidation occurs if the soil has been covered by a thick overburden. So if the soil has been covered by a thick overburden, then the soil has to be considered as over-consolidated soil. So depending on this, generally even in Sri Lanka, we can use this type of values. So, but if it is a good soil, over-consolidation ratio is between 3 to 5. This ratio is 400. And CU value is 75. 75 multiplied by 400 divided by 400. Now you will see the horizontal subgrade reaction is 30,000. Horizontal subgrade reaction is 30,000, and it's a pretty good value. It's a pretty good value. Because if you get a value like 2,000 or 4,000, then it's a low value. And if you are going to have 1 meter diameter piles, then the horizontal subgrade reaction will be, and also you are having springs every 1 meter depth, then the horizontal subgrade reaction will be 30,000 multiplied by 1 multiplied by 1. On the other hand, if you have a pile of 1.2 diameter, then ES divided by 1.2, and then again you will find you can find the value of ES. Likewise, again you will find that the horizontal subgrade reaction does not depend on the size of the pile. It is a constant value. So because what happens is, if the pile is 1.5 diameter, you get ES is 1, ES divided by 1.5 is the case. But when you multiply it by the area, again you are multiplying by 1.5 multiplied by 1. Again, you will end up with ES. So basically, and also this value does not vary with the depth of the soil. So if I stop share and if I show you how this can be modeled, so this is 30,000. This is 30,000. But that is not the case you get in sandy soils. Sandy soils, it increases. It is increasing all the time. And in sandy soils, it increases with the depth. Whereas in over-consolidated clay soils, it remains the same. It remains the same. Whereas in the case of sandy soils, we might start with 20,000. And at a certain depth, you might get even 100,000 or 200,000. So sandy soil, the behavior will be very much different. The sandy soils can actually exert a huge resistance against deformation, whereas clay soils cannot offer a huge resistance against deformation of the pile. So it's a constant value like 30,000, or it can be even less than like 20,000 or even 10,000, depending on the plasticity index of the soil. And whereas in the case of sandy soils offer pretty good resistance against deformation. So you will get much favorable conditions with sandy soils. So sandy soil can be one where you have laterite soils, but the water table is low. Clay soil is one, you have laterite soil, water table is high. On the other hand, we can sometimes encounter real clay soils as well. But clay soils, we all know, not very strong. So that's why, you get the value of resistance to deformation does not vary with the height of the soil. Whereas in the case of sandy soils, it varies with the height of the soil. Bandhuka, is that all clear?
Yes, sir, that is clear.
Right. So basically, if I share the note again, right? So basically, now these values are represented as a chart as well. And then when you have sandy soils, I told you that it increases with the height. So here you can see Z is the depth, D is the diameter. D is the diameter of the pipe. NH is the coefficient of modulus of variation, modulus of variation in kilonewtons per meter cubed, and Kn value. Oh, sorry. Yeah, sorry. I shared. Shared. You are not getting it?
Now it is okay.
Now it's okay. Yeah, sorry. I probably I am pressed the wrong key. So basically, K is the modulus of upgrade reaction in kilonewtons per meter cubed. NH is the coefficient of modulus variation in kilonewtons per meter cubed. This is the depth from top of the ground level in meters, and D is the diameter. And so again, a lot of geological research has happened. So a lot of people have given different formulae, but this is again commonly used one. N value less than 4 is really bad soil. Friction angle is less, and relative density is less than 15 and very loose sand. Then if it is 4 to 10, you get loose sand, but friction angle is higher. And when the sandy soil becomes very stiff, the friction angle can be high. And then relative density also is given with some value. And when it is over 90, we call it very dense. Now you can see how these values can be used in finding the Ks value, NH value, and right here you can see. Here you can see. On this side you get NH in meganewtons per meter cubed. So you have to multiply this by 1000 to convert it to kilonewtons per meter cubed. And now you can see, depending on the N value, you can decide what is the relative density. Now let's say we are in this range, and we are going to say the relative density is, say we are around 15, and we are going to say the relative density is about 65%. 65%. So what you do is you come to this chart, go along the 65% line, and if the sand is below water table, you will use this chart. If the sand is above water table, you will use this chart. From this one, if the sand is above water table, you will get a subgrade reaction of about 45,000. And here you will get a value like 25,000. So let's say the value is 25,000. If the value is 25,000, then what you do is you will come here 25,000. Now, if the diameter is 1 meter, depth is 10 meters, what will happen? 25,000 multiplied by 10 divided by 1. So you get 250,000 kilonewtons per meter. And then you have to multiply it by the area of the pipe. So that means if it is a 1.5 meter pile with 1 meter, a spring every 1 meter depth, then you have to multiply 250,000 by 1.5. So now you can see in sandy soils, as the depth increases, you get massive resistance against the deformation of the pipe. Massive resistance against the deformation of the pipe. So, whereas in the case of clay soil, it does not vary with the depth. You get only about 30,000. And so whatever the value, the important thing is, once you create a computer model, you can generate all the different load combinations that can occur during the construction and also during the service, because during the service there can be breaking loads that are transferred to the piers, and through the piers, the breaking load can be transferred onto the piles. So if you like to know how the piles are going to react, then modeling the pile alone is not enough. You have to model the pile and you have to model the soil as well. To model the soil, you need to know the horizontal subgrade reaction, and depending on the type of soil, you can find it. And also for laterite soil, you will always look at whether the water table is high or low. If it is high, you will consider it as a clay soil. If it is low, you will consider it as a sandy soil. So I think we have covered a reasonable ground on that. And then in the case of rock, if you know the RQD value, and then you can always use some of these curves and get a value. But generally in the case of rock, these values are extremely high, maybe maybe in the range of 500,000 kilonewtons per meter squared. So basically in rock, the resistance for lateral deformation is extremely high. So generally in the range of 300,000 to 500,000 kilonewtons per meter squared or more, meter cubed or more. But so basically, if you have anything in the rock, nothing to worry, it's not going to deform. But if you are having soil, you can see in the first 1 meter and 2 meters, if this value is 25,000, the resistance may be only about 25,000, varying from 0 to 25,000, which means the average value is about 12,500. In the next 1 meter, 2 meter, the average value may be about 37,500, and then likewise it goes on. So basically, in the second meter to third meter, you get an average value of about 62,500. But those can actually indicate fairly high level of resistance. And then the other important thing is how the pile behaves and what will happen to the pile when you do this type of modeling. So I'll stop share, and now you can see we are having a structure. I'll use a line structure. So it's like that. It comes light, and then we have pile foundation. We have piles. Now we are having very peculiar loading conditions like bending moments acting here. What will happen? The piles also will be subjected to some kind of bending moment. So generally you will find the bending moment in the piles. There can be bending moments in the piles, but these bending moments actually disappear at a depth of about 3 to 4 meters. Within the first 3 to 4 meters, these bending moments become almost zero. So that is the good news, because although the pile can be subjected to bending moments, these bending moments will quickly disappear and they become negligible at a certain depth. And then when you look at the behavior of the pile is a member subjected to axial compression. So it's a pre-stressed concrete member, because any member subjected to axial compression can behave like a pre-stressed concrete member. And we all know pre-stressed concrete members have a huge moment carrying capacity. So because of that reason, even in the highway piles, you can have about 1% reinforcement up to about 12 meters. And if you want, you can reduce it to about 0.5% beyond 12 meters. Beyond 12 meters, you can easily reduce the amount of reinforcement to about 0.5 meters, 0.5%. Because these days steel reinforcement is pretty expensive, running close to 400,000 rupees per ton. So the reinforcement cost is around 400,000. So, no need to unnecessarily dump lot of reinforcement, bury lot of reinforcement in the ground, knowing very well the piles are not subjected to bending moments beyond 4 meters. And anyway, within the first 9 to 12 meters, we can anyway have one length of reinforcement, because reinforcement can be bought 6 meters, 9 meters, or 12 meters. And when we were students, 40 years, nearly 35 years ago, or more than 35 years ago, when Professor B.L. Tennapan taught us pile design, he said piles need only 6 meter length of reinforcement. Right, so that's how we learned about piling. But later, it became the practice in Sri Lanka. A lot of engineers put a lot of reinforcement into the pile until we even going into the bedrock. But very capable engineers have designed a lot of pile foundations where they have omitted the reinforcement, showing that the pile is not subjected to any bending moment. But in the case of bridges, I don't mind having some reinforcement, because the scour damage might expose the piles unnecessarily, and that might endanger the pile. So it might be a good idea to have some nominal reinforcement, considering that the pile is a lightly loaded reinforced concrete structure. And for lightly loaded reinforced concrete structures, the Eurocode specifies 0.2%, but Eurocode also specifies a minimum reinforcement of 0.5% for piles if you are providing reinforcement. So, because in the case of piles, we need to have a certain amount of minimum reinforcement, unless otherwise you can't, you don't get sufficient strength in the piling cage. So you can't maneuver the piling cage unless you have enough reinforcement. So because of that reason, 0.5% might be a good idea. But whereas in the upper part of the pile, you can go for 0.8 to 1%. And I have seen Road Development Authority engineers like 1% reinforcement in the piles. So that's a kind of information I can give you. Only thing is, I have not shown how exactly to do a model on SAP 2000 type program, but I have shown you how we have done modeling for buildings. But now I have talked a lot about piers. Next day I will talk about abutments. I'll talk about abutments. So Banduk, any questions that we can?
Yes, sir. There was one question in the chat box.
So what do you think about reducing the pile length based on board pile sample with higher point load? Can the pile group in same length to avoid differential? Okay, now basically I would say something very important, right? And so when you are talking about pile group, I mean, to have a pile group, it has to have a lot of piles. But this is something that you have to keep in mind. Now, let's assume that let's compare the case of a bridge consisting of I-beams versus the same bridge done with 2 box girders. So these are 2-lane bridge with pedestrian pavement. Now, when you are designing, you have to consider that the loads will act here, loads can act here, loads can act here, loads can act here, all the locations. So that means each beam will be designed for a significant amount of load carrying capacity. Whereas you have the whole HP vehicle here or the whole HP vehicle here, you are going to design the bridge only once, one beam once. Whereas, so if you calculate the total sigma force carrying capacity of these beams, it can be F1, sigma F2. You will find sigma F1 is much higher than sigma F2. Why? Because each beam is going to have a lot of overstrength, whereas these ones will not have that kind of overstrength, because we analyze it once and we decide it for one set of loads. So when you move from this to this one, you can actually, if you want, you can reduce the number of piles very significantly, because we are now carrying much lower load on this system than the ones due to this. So when you go with lesser number of beams, you can end up with lesser number of piles. When you have only few piles, and when they are at a spacing of 3 times the diameters, I think you don't have to consider the group effect. You don't have to consider the group effect. And the other important thing is, that's a good question that has come up. Yes, it's true. We put the springs into different directions. When you are adding the springs, you will put the spring in X direction, and you will put the spring in Y direction. Because we cannot, we have to, we really, because when you are doing 3D modeling, the springs must be applied in 2 different directions. That's a second question. Or maybe the same person. Or Hashmi, AM29648 has asked. Second question is by AM257. It's the same person asking. Oh no, different person. 25798, right? So you have to actually apply horizontal springs in two opposite directions at 90 degrees. And also, so basically, when you are doing piles, especially for bridges, because we are going to have some climate change induced severe changes in our weather patterns, I would recommend, if you are going for piles, don't terminate them at high levels. The reason is, these days in Sri Lanka, we have plenty of machines that can easily allow the pile to go into the bedrock. Because we are not going to, we really don't know the exact river characteristics that will occur in the future. So because of that reason, I would prefer going up to the bedrock if you are going to have bridges on large rivers in Sri Lanka. And if it is a flyover, then you can even consider a raft foundation. So next day I will show you how to model a raft foundation for a flyover, provided the laterite soil or reasonably good stiff soil is available. So I can show that as well. So with the abutment, we'll talk about how to model the soil with the abutment, assuming that it's for a flyover, or assuming that the abutment is away from the floodplain. So the chances of covering is very little. But because we are constructing a bridge much wider than the river to allow for flooding. So considering that, I will explain next day the abutments and how to deal with pipe foundations, and also how to deal with clay type of foundation, where we are going to model the abutment along with the soil. So those are things we can discuss next time. So Bandukha?
Yes, sir. Okay.
Yeah. So I think time is almost up, and
Okay.
anybody having any other question, I can answer.
seems there are no more questions.
Yeah, okay, then in that case, we can wind up.
Okay. I would like to invite Engineer Mangalasiri to deliver the vote of thanks.
Thank you. Good evening to all. Thank you all for staying with us this session with lots of learning. Today was the 15th session of the webinar series on structural design of highway bridges. On behalf of the organizing committee, I would like to express our heart gratitude to Professor Teshan Jayasinghe for informative and valuable presentation. Dear sir, we highly appreciate your effort and time spent on enlightening us.
Yeah,
Then,
thank you.
I would like to express my sincere gratitude to CESC Chairman Engineer Kamala Gunawardena, ISS Secretariat, the Publicity Department and IT team for their valuable support and encouragement to success this webinar series. Also, today we had more participants, so we really appreciate your participation. Finally, as I said, the next session will be held on next Tuesday, that is the 20th of June. So we hope to see you all there. Thank you. Good night.
Okay, good night. Thank you.
Thank you, Engineer Mangalasiri. Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.